Welcome to The Explainer. Today, we are diving deep and demystifying one of the most powerful ideas in all of modern tech, neural networks. We're going to find out how a computer can actually learn, starting from just one single artificial neuron and building all the way up to a program you can actually code yourself.
You know, it all really starts with our inspiration, the human brain. For decades, computer scientists have looked at this just unbelievably complex network, and they've asked this one fascinating question. Could we build a computational model that's based on the brain to solve problems that traditional computers find, well, almost impossible?
And this right here, this is the core problem they were trying to solve. You see, a traditional computer program, it can calculate the square root of some massive number in like an instant. But ask it to do something a toddler can do, just spot a puppy in a photo, and it completely struggles. Neural networks, they were designed to bridge that exact gap.
So how in the world do you even begin to build an artificial brain? Well, you start with the smallest possible piece. We're talking about the original artificial neuron. It's this beautifully simple concept from way back in 1957 called the perceptron.
Just think of it as one single tiny computational cell. It takes in a few pieces of information, does a super quick calculation, and then makes a really simple decision. Yes or no, on or off. It's totally designed to mimic a biological neuron, which, either fires off a signal or just stays silent. And the process is, well, it's surprisingly straightforward. First up, every piece of input gets a weight. That's just a number that tells you how important it is. Second, you take all those weighted inputs and just add them all together. And finally, that sum gets passed to what's called an activation function. And that's what makes the final call. Fire +1 or don't fire -1.
Okay, let's put some actual numbers to this to see it in action. Let's say we have two inputs, 12 and 4. We multiply them by their weights, which are 0.5 and -1. That gives us 6 and -4. Add those together, and the sum is 2. And since 2 is positive, our activation function spits out a +1. See, that's really all there is to it.
But here's the catch. A perceptron isn't very useful if its weights are just a bunch of random numbers. The whole point is for it to get smarter. It needs a way to learn from its mistakes and actually improve its guesses over time.
So how does it learn? Well, believe it or not, it's with this beautifully simple formula. You just take the answer you wanted it to give, the desired output, and subtract the answer it actually gave. And that result? That's the error. It's just a single number that tells the machine exactly how wrong its guess was.
And that error value, that's the key to everything. It's used to slightly tweak the weights. It's kind of like constantly correcting the steering wheel on a car to stay on course. Every single time the perceptron makes a mistake, that error just gently nudges its weights in the right direction, making it just a tiny bit smarter for the next guess.
And this process, this is what creates a training loop. You feed it an example, it takes a guess, you figure out the error, and then you adjust the weights. And then you do it again and again. You just repeat this process over and over, and with each cycle, the network gets progressively better and better at its job.
But a single neuron, as clever as it is, has a pretty big fundamental limitation. There are certain types of problems that it simply cannot solve, no matter how long or how hard you train it. See, a single perceptron can only solve problems that are, and this is a bit of jargon, linearly separable. Now, that's just a fancy way of saying you can divide all the yes answers from the no answers with one single straight line. But for more complex problems, like something called the logical XOR, where one line just isn't enough to separate the groups, well, a single perceptron is completely stuck. And the solution to this is it's so elegant. Instead of just one neuron, we use a whole network of them. By connecting these perceptrons together in layers, you've got an input layer, one or more hidden layers in the middle, and then an output layer. We create a system that can solve much more complex problems. The network as a whole can learn to draw these really complex boundaries, not just one simple straight line. But wait, how do you train a whole network? That sounds complicated. Well, the process is called backpropagation, and it was the huge breakthrough that made these deep, complex networks truly possible. Basically, it takes the final error from the very end and feeds it backward through every single layer, adjusting each weight along the way. Now, the math underneath is pretty complex, but the core idea, it's exactly the same. It's all about learning from your mistakes.
All right, at this point, you might be thinking, this sounds incredibly complicated to code from scratch. And you know what? You'd be right. But fortunately, there are amazing tools now that handle all the heavy lifting for us, making machine learning accessible to everyone, not just people with PhDs. And a fantastic example of this is a library called ML5.js. It's built on top of Google's TensorFlow.js, and it's specifically designed to be super beginner-friendly, especially for artists, creative coders, and students. The best part? It runs right in your web browser and handles all that complex backpropagation stuff behind the scenes, so you can just focus on being creative.
And using a tool like this follows a pretty standard workflow, really for any machine learning project. First, you collect your data, then you prepare it, get it all formatted nicely, you choose your model, you train it, and then you evaluate how well it did. And finally, you deploy it so it can start making predictions on new stuff it's never seen before.
Okay, let's make this real. Enough theory. Let's actually walk through building a simple program that can recognize the direction of a mouse gesture. So up, down, left, or right.
First things first, we need data. This is the raw material for learning. We have to create examples to teach the network. So for each gesture, we'll give it the inputs, the X and Y direction, and then the correct label that we want it to learn, like right or up.
Now, with ML5.js, this is where the magic happens. We can create and train our entire neural network with just a couple of lines of code. Seriously, one line sets up the network and the next one tells it to start learning from our data. That's it.
Okay, so once it's trained, our model is ready to go. Let's give it a new input, something it's never seen before. A vector that's pointing straight to the right, and look at that. The model predicts the label is right with over 96% confidence. It actually works.
So we've gone from the inspiration of the human brain all the way to a working classifier. We've seen that the core of machine learning is really just about a simple loop. Make a guess, measure the error, and make a tiny adjustment. And by repeating that process, a machine can truly learn. And that, well, that brings us to one final, really exciting thought. Now that a computer can learn, what will you teach it?